Here are the syllabus statements for electric fields. I'm going to kind of break it into two parts, forces and energy. Feel free to pause it at this point and have a read over those points there. First of all, though, we need to recap what we did at AS, which we can see over here. You started off by defining what an electric field was, and this is a field of force. This basically tells me if we have say a positive charge here, that this creates a field around it, that's kind of an invisible area, and each point in this field will experience an amount of force per unit charge you put there. So if say we're putting a positive charge here, how much force does it experience will tell you how strong that field is. This field only acts on charged particles. If I put some mass here, which is neutral, it's not going to experience any force. However, it will experience obviously a gravitational force because that's a different type of field that acts on masses. We represent fields with field lines, as you know, magnetic fields, gravitational fields, which are lines with arrows showing the direction of the field. The direction of the electric field is the direction of positive charge we're moving, so it's from positive towards negative. E is the electric field strength. It's important to define how strong a field is, because that's useful to know how much force something will experience. Again, let's imagine we have a positive charge here creating a field. Let's say we put a 1 coulomb charge into the field over here. If that 1 coulomb charge experiences 1 Newton of force, then the electric field strength comes from this equation, E equals F over Q. It's the amount of force it experiences divided by the charge of that particle that we put into the field. So that would tell me the electric field strength at this point is 1 Newton per coulomb. It also has units of volts per meter, which we'll see where that comes from in a second. It's over here. And you could also prove that these two are equal as well. The definition is the force per unit positive charge. With gravitational fields, it's just the force per unit mass, because there's only one type of mass. In this case, there's two types of charge, so we need to find which one we're referring to. We also looked at uniform fields last year, which are created when we have two parallel plates. And look at this lovely uniform field there, not drawn very well by Sir here. These should be equally spaced and parallel. But this shows it's uniform. What does that mean? Neil, I'm already getting hungry. Wherever we go in this field, there, here, a charged particle is going to experience the same force. So say we put 1 coulomb into the field here, it will experience the same amount of force. And we have an equation to calculate what the electric field strength is between these two plates. If you divide the potential difference, so say this was plus 2 volts, this was 0 volts, so the potential difference here would be 2, and divide it by the distance between the two plates, that's D, distance between plates, you get the electric field strength. Note this equation only applies to uniform fields. So, let's go back to our syllabus. We've now recapped AS. We're going to start by looking at forces over here. Let's imagine we have two charges, spherical charges. One's plus 2 coulombs and one's plus 3 coulombs. They're both going to exert a force on each other. The force is going to be equal in size but opposite direction because they repel. We know that. That's just a rule of the universe. You're going to have to get over that if you don't like it. How can we calculate the force? Because that's useful to know. You never know when in life you'd want to know the force between two charged particles. Well, luckily, Mr. Coulomb has done all the hard work. This equation here tells you the size of the force. If we know the charge of the two particles, in this case plus 2 and plus 3, times those two together, and then divide by 4 pi epsilon naught, which is a constant. Epsilon naught being the permittivity of free space, which is on your formula sheet. And it just tells you how easily the electric field permeates through free space. It's using the name. R squared, well, R is the distance between the two charges, and we'll see what we mean by distance in a minute. Don't forget the squared. It's a vector quantity because it's a force, so that's important when doing questions. This also can be written as F equals K, Q1, Q2 over R squared. What is K? Well, K just refers to all those constants wrapped up in a nice little package. Looks much neater, but also shows you the similarity between that and gravitational fields. You can see here, the G is the constant that relates the masses and R squared to F, but in this case it's K. Crazy, eh? Right, a few things to consider, but what are we referring to? What distance are we going to use when we've got two charges like this? Do we measure it from there to there? No, because we can consider these to be point charges. So just imagine that all this sphere is condensed down to one point of plus 3c. And therefore r will be that distance over there. What if we have a positive and negative charge? Good question I hear you ask there. Well, that's going to give you a negative force if you put that into the equation. Don't worry, all that's telling you is that they are attractive. If you get negative answer, it tells you the two forces are acting towards each other and they're attracting in. You'd only get that when you have opposite charges. If you have two negative charges, obviously the two negatives times together will give you a positive, showing you that they're repelling. Let's come back over to our syllabus statements. You can now see we've covered this one and this one. And now let's have a look at this one, which again relates to force, but we're going to consider a point charge and get an equation for the electric field strength. So we know how to work out E for uniform fields. Oh, look, there it is, just at the top right there. What do we do about point charges? I.e., what is the electric field strength at this point here created by this charge? Remember, it doesn't matter what we put here. The field strength is determined by this charge. This is the one making the field here. So what strength will that field be at that point? Well, the good news is we have the defining equation for this, E equals F over Q, which we mentioned earlier. If you divide the force by the charge, this equation applies to all electric fields, uniform and point charges, radial fields. And if we substitute this, which is Coulomb's law, into here, you can have a go at that, but you'll see that the Q's cancel, and you're left with this equation here. You need to learn this one. Don't forget the r squared, because people get that mixed up with the next one we're going to do. And remember, this only applies to point charges. That's really important. It's a vector quantity. So say we had positive charge here, positive charge here. Both of these are going to create an electric field at this point. This one's going to be acting in that direction, and this one's going to be acting in that direction. It'd probably be a bit smaller if this was the same charge, 1 coulomb and 1 coulomb. So to find the resultant, you need to use that equation to find the size of E here and here, E1 and E2. And then you'd have to do vector addition to find the resultant, because actually it would be somewhere in that direction. Oh, I love those questions. Do practice them though, they are tough. So that's that one there. And we've kind of covered all the areas around force. Notice that if it's to do with force, remember this is the amount of newtons per coulomb, and this is the number of newtons, then we have an r squared involved at the bottom. We're now moving on to energy, and as you'll see, there's no r squared. It's a common mistake in the exam. So let's define what potential is initially, and then we'll have a look at the equation for potential, and then talk about what this point here relates to about the potential gradient. So, energy, what's this all to do with? Well, energy is an important concept in physics, and we can define the amount of energy per charge at a point in a field with the concept of potential. You might recognise that name, potential difference, voltage, and it has the same symbol, capital V. The units are the same. It's a volt, which is equivalent of a joule per coulomb. Best to write it like this, though, because this really teases out what it's telling you. It's the amount of energy per unit charge. What is potential? Well, first of all, we need to find zero somewhere. I mean, is it under the back of your sofa? Well, no, that's not very useful for physicists. And the only place where it really is zero is at infinity. So, very similar to gravitational fields, we define V is 0 at infinity. We're going to imagine we've got a positive test charge over here. A test charge is just a charge that doesn't... we'll just imagine the charge on it is so small that it doesn't affect the field. It's a hypothetical thing. Because obviously, if I move this, it has its own field, which would affect what we're trying to say. And we want to know what is the potential at this point over here. Well, the definition is it's the amount of work done, okay, because in this case I'm doing work. Sometimes the field will do the work, in which case you'll get a negative answer, but in this case I'm doing the work, because I have to push this positive charge in. Imagine this little fellow here is positive. I'm pushing, doing work, using up energy. It's all getting stored in the electric field. And as I move to that point there, I've done an amount of work. It might be 20 joules. Let's say I did 20 joules of, So I did 20 joules of work going from that point. And this is poly, the positive test charge, which has a charge of 1 coulomb. Is the charge. How do we work out the potential? Well, the definition of the defining equation, which we'll look at in a minute, is the amount of energy per unit charge that we moved. So 20 divided by 1 will tell me that the potential at this point is positive 20 joules per coulomb. Obviously, this is going to depend on the distance from this charge. So if I keep that distance constant, and I move poly over to here, I'd be doing the same amount of work. It's the same distance away, so I've had to push it against the same repulsion from that. Now, V does not depend on the charge of this. Okay, it's a property of the field created by this charge here. Doesn't matter what I put into the field, because it's divided by charge, it kind of cancels out that charge. It only depends on the thing creating the field, this charge here. I mean, if you think about it, that's actually quite a tricky concept. Let's just talk about it a bit more. Let's imagine we moved, whoops, oh, I can't now move that, but imagine I moved that charge over from here. So this positive charge came from over here, but this time it had a charge of 2 coulombs. Well, as you can imagine, when I move it to that point there, it's going to, because it's got twice the charge, I'm going to have to do twice the work. So it's going to be 40 joules of work. But when I put it into this equation over here, again, 40 divided by now twice the charge, we'll get the same potential at that point. So it doesn't matter about the charge we're moving into the field, it just matters about the charge there. It's quite useful to know this, because if I now let go of Polly over here, she's going to go flying back over to here, and we know how much energy would get back. 20 joules per coulomb of charge there. So the definition's there. Feel free to write that down. Don't forget you need to mention positive charge, because we need to define which charge we're referring to. And the idea that it's coming from infinity to a point in the field. Defining equations over there, which you would have touched on in GCSE. But there is also an equation which you can get by integrating. And that is this one. You don't even need to know this. It's on your equation sheet, and you don't need to know where it comes from. But it tells you the potential at a point depending on the charge of the thing creating the field, divided by 4 pi epsilon naught, and r is the distance between the point and the centre of that charge. It's a scalar, which means when you add them together, you can just do simple addition, no need for vector addition. Let's have a look at some examples here. There's a positive charge here at the centre. It's creating a field shown by these black lines. We've got these green dotted lines. These are called equipotential lines. Ooh, I wonder what they mean. Clues in the name. Equi, equal, potential, potential. So anywhere along this line here, will have the same potential. Delta V, as I move across here, will be 0. So actually I can do that for free. That will just move around there, and I won't need to put any energy in. These equipotential lines have values, and we could use that equation up here to work out the size. Let's imagine that this one here was plus 1 volt, plus 2 volts, plus 3 volts. And of course, where's 0? Oh yeah, right out an infinity, V would equal 0 volts. This is a negative charge, so if we put a negative into there, we'll get negative potentials around it. So it'd be -1, -2, -3. What's useful about this is obviously you can see this quite visually now. If I moved, say, let's get a red pen here, 1 coulomb of charge from there to there, the change of potential is 1 volt. And that's quite useful to know, because then we could also work out the amount of work I need to do that. That's going to be the change of potential times by the charge moved. So we know that we're moving 1 volt. We're moving between here and here, so that's a change of potential of 1 volt, and the charge we moved was 1 coulomb, so we know that we're going to need 1 joule of energy to do that. Likewise, if we move that way, we'd get 1 joule back, and that would become kinetic energy there. That is cool. What about uniform fields? Well, they're a bit easier. You can see one here. Let's say this is plus 3 volts, this is earth at 0 volts, and we see the equipotential lines coming down here, equally spaced, because the field's changing out of, the field's uniform there. If we think about Polly again, the positive test charge over here, moving from this plate to this plate. Remember, it's positive, because that's the definition. And if I put Polly there and let go, she's going to move pretty quickly over to this side. She will accelerate, but the force remains constant. F equals ma, constant resultant force, means constant acceleration. So speed will increase over to this side. We can also think about the potential with distance from that point. If you look over at this graph here, you can see we've got potential plot against distance. Well, the potential energy is going to change at a constant rate. Now, this is kind of the wrong way around, which is kind of confusing things, because this would be the 0 volt bit moving towards the plus 3 volt, because we're getting more and more potential energy stored. As I move Polly, the positive test charge, from there to there, I'm repelling, that energy is getting stored as potential energy. It's changing at a uniform rate, because with distance, that is, not with speed. And as we get over to here, that's all stored as potential energy, released as she moves from there to there. Okay, we've mentioned about where V is naught, that's the at infinity. Right, let's look at the potential gradient, which is that last syllabus point we're going to look at before we look at comparing it with gravitational fields. What is potential gradient, first of all? Well, the clue's in the name. It's the gradient of the potential. The gradient of a road is how much meters it goes down as you go 1 meter across. In this case, it's how the potential changes with each meter that you move along. This can kind of be visualized using a potential well like this. Imagine we have a big, fat, negative charge down here. And it's creating a potential well, similar to the gravitational potential wells we looked at. At the surface here, at infinity, imagine this infinity, we've got zero potential. And as we go deeper down, because there's negative charge, remember these are negative potentials. And look, I've even done my lines quite well here, getting more and more spaced. Oh no, I haven't. That's evasive of me, I've done it the wrong way around. They should be, good lesson learned there, should be close together here and then getting more spread out as we go that way. Why? Well, if you look over here, you can see nearer the thing they're close together and they get more spread out as we approach infinity. It's related to the 1 over r proportionality in the equation. So, what's going on here? Well, if we think about this, the steeper the well, so how steep this drops in, the stronger the field's going to be. Because if we have a huge, huge, huge charge here and a huge field, this is going to be a much steeper well. But the steepness of this well is basically the potential gradient, because every meter we move that way, how much does the potential change by? So we can relate this to, I mean, you can see I've drawn a nice little chart there. If I made this stronger, the well would be steeper. So we can relate this steepness of this well, or the potential gradient, to the strength of the field. And it's just E, the electric field strength, is equal to the potential gradient, which is over here. There's also this weird little negative that comes in. Well, this negative is just to get the direction right. If we imagine a positive charge up here falling into this well, it's going to be attracted in. Now, the potential gradient in this case is negative, because each sort of meter we move towards it, we're going down to a more negative potential. And the electric field strength is also going to be in the same direction. So that's what brings in that negative there. You can also think about it in terms of a positive charge moving towards a positive, bigger charge over here. As this positive charge moves towards it, the potential gradient is going to be positive. And thanks to the negative, that tells us that the electric field is going to be in the opposite direction. Well, yes, it is, because we know electric field strength goes from positive away from positive charges. An example question that they might ask, they might give you a graph of potential against R. We know the shape of this because it's proportional to 1 over r. And they might ask you to find, say, the electric field strength at 1 meter away. So we go to 1 meter, we dot up, and we draw this lovely tangent to the line there. We then find the gradient, remember using a nice big triangle and showing the triangle to the examiner. Find the change in y, and divide it by the change in x. Because that is equal to the change in v, divided by the change in r, which is the potential gradient. Delta v over delta x, or delta v over delta r, is the potential gradient. Once we have that, the gradient, if we just put a negative in front of that, that will give us the electric field strength. So let's go back to our syllabus statements, which you can pause and look through, but we've now done all of these down to here. The last one is kind of just a recognised sort of thing where you just got to do some sort of fun hippie stuff about the similarities between electric fields and gravitational fields, which are really interesting. I made a very brief summary here, but you can flip back to your notes and look at other things here. But just some real key quick changes, quick differences between them. Gravitational fields here, electric fields. What do they originate from? Well, gravitational fields is from mass. Anything with mass creates a gravitational field. And anything with charge creates an electric field. So a proton creates both fields. Fun, but they're independent of each other. The field strength is the amount of force per unit mass for gravitation, and it's always attractive. A big difference for electric fields is the field can be attractive or repulsive. But look, the defining equation is pretty much the same, but depends on the fundamental part of electric fields, which is charge, is the amount of force per unit charge. For point charges or radial fields, so remember radial fields are ones that go out radially like this, a bit like the road network around the CBD of Auckland, which is kind of radial. You've got the motorways coming out, Harbour Bridge going that way. It's kind of a radial road network there. We notice that the force for both is proportional to 1 over r squared, so a very big similarity there. And for potential, again, very big similarity that we define zero potential for both of them at infinity. And again, notice how the potential, gravitational potential over here, and electric potential over here is proportional to 1 over r. Hope you found this video interesting and useful. Definitely interesting. Don't know whether it's been useful. Here's the syllabus statements for you to check that you understand all these. Please do ask if you've got any questions. Thank you.